Right, so last time, unfortunately, we had this system crash. However, I'm glad to say that they carried on recording the audio and what was on the screen, though I wasn't able to write on the screen. And I think that all our problems have been caused by the fact that I was trying to run it on batteries during all these complicated technology. So I'm going to be using the power cable from now on, and hopefully that will solve the technical issues. So at the end of last time, we were having a look at these few sets, and I told you the answers as to what the interior points and the non-interior points were. I may have said at least one of them wrong verbally, but here I've written them down correctly. The interior of the empty set and the interior of the empty set were both empty. And then we had the next set, which we talked about. The only non-interior point of R plus, the only non-interior point of R plus was the point 0. For the rationals had no interior points, and the complement of the rationals had no interior points. So the interior of Q is Q, and the interior of Q complement is Q complement. And the interior of the whole real line is just the whole real line, whereas the interior of the whole real line was the empty set. And I left it to you to check the details of all of those. And now that we understand the interior and the interior, we can talk about the open sets. Now this is very important when it comes to complex functions and complex analysis. In next semester, you'll be dealing with open sets almost all the time. So it's very important to be able to recognize which sets are open and which sets aren't, though in the complex functions, you'll basically be dealing with sets in 2 dimensions only. But since our definitions will work in all dimensions D, we'll do that. In fact, as I mentioned before, most of our definitions work whenever you've got any set with a notion of distance on, because that's all we needed to define the open balls and the closed balls. So we've got a subset of R to the D, and we try to decide whether it's open or not. Open just means that all of its points are interior points, which informally means that, formally in this module, it means that it doesn't have any non-interior points in the set. Now, what are non-interior points in the set? Those are points in the set that are at its edge. So, to be open, there mustn't be any points in the set that are at the edge of the set. In some, that's slightly informal. So you're open if the interior view is the whole of U. Every point is an interior point. By the way, we know for free that the interior view is a subset of U because that was part of our definition. So all you have to do is show that U is contained in interior view. That's why you just have to check that every point of U is an interior point to check that it's open. And if you're not open, not to be confused with a word coming up later called closed, which everybody gets mixed up with not open. They're completely different concepts. Well, almost. Not open means that this thing isn't true, which means that not every point of view is an interior point. That means there's at least one point of view which isn't an interior point of view. And that means there has to be at least one non-interior point. So U is not open. A very important term to know, not open, because that's the correct negation of being open. If and only if int of U is not empty. There must be at least one point of view which is at its edge. At least one point of view which is a non-interior point of view. So let's think about some examples. First of all, here's a full definition with an R in it. This is the standard definition of open that you'll meet in many of the textbooks. So a subset of R to the D is open. That means that for every, or for each, that's the same thing, for every x in U, there is an R greater than naught, so that the operable centered on X is contained in U. This last bit says that X is in the interior of U. So if you note that that last bit says, which includes this, that last bit says X interior of U, so I've just written it out in full. It's every X in U is an interior point of view. Now, of course, as you get nearer and nearer the edge of U, if you can, then you're going to have to take smaller values of R to avoid leaving the set. This R is, roughly speaking, the distance to the edge of the set, or something slightly smaller than that, just to make sure that you don't go outside the set. So if you take an open interval in the real line, say going from A to B, well, we've already looked at examples of this. It's clear from the diagram, it's clear that every point of this open interval is a non-interior point, is an interior point. The non-interior points would have to be at the ends of the interval, but they're not in the set. So if you have U equals AB, where A smaller than B is a real number, so say A smaller than B in R, and U equals the open interval AB, or with the alternative notation, then clearly from the sketch, I'll accept that U has no non-interior points. So we have the interior of U is equal to U is equal to the open interval AB, and the interior is empty, and so U is open. This is good news, because if an open interval wasn't open, we'd be in big trouble. But half open or closed intervals are not going to be open, because they're going to have non-interior points, unless, of course, they happen to be empty. So let me draw a typical example of a closed interval. So let A and B be in R with A smaller than B. Then AB, the two half-open intervals, see, we haven't completely resolved the technical issues. The two half-open intervals and the closed interval are not open because none of them are equal to their interior. Each of them has at least one non-interior point. So just to specify a little bit more, the interior of AB is just the point B, because A is not in the set, so it doesn't count. But the interior of the other one, which includes A but it excludes B, that's just got one non-interior point at A. Of course, these sets are non-empty. and the interior of the closed interval has got both endpoints in it. So none of these three sets are open. So, to be very careful, these three sets are not open. Which I actually said already. Now, I said open intervals are open, and I explained why. An open ball in R to the D is open. And I really hate having to prove this, but we called it an open ball before we defined what an open set was. So if you look at the module FAQ, you'll find out why you have to prove that open balls are open. Because we just called it open, and to say something is open because we called it open is not entirely satisfactory. So I'll draw you the picture in R squared, and then we'll base our proof in R to the D on that. So you take a typical ball in R squared, it'll look something like this. So this is the open ball, radius capital R, centered on the point A. And the claim is that this so-called open ball is actually an open set. To prove that, you have to prove that every point of this open ball is an interior point of the open ball. So you have to show that it's got no non-interior points, or that every point of it is an interior point. So if you take a typical point out here, X, that's in the open ball, you've got to prove that it's in the interior of the open ball, which means you have to be able to draw a little ball around that. So we need, now I haven't written out a formal proof here, but I'm just giving you some idea. We're going to write the formal proof out in full in a minute. We're going to need the open ball centered on x radius little r to be contained in, just move that over a bit, to be a subset of the bigger open ball. Radius capital R centered on A. Now I usually would let you think about this sort of thing, but because we started a bit late today, I will, for once, just give you the answer that we need a positive real number little r that will do this, and we'll see that any little r with naught less than little r less than or equal to big R minus norm of x minus a will do. And that's because, obviously, the distance from the point x to the edge of this ball is going to be capital R minus the distance of x to a. Let me just draw in that distance there. That distance, distance to the centre, that is norm of x minus a. So to get out of the ball, you'd have to go at least another capital R minus norm of x minus a to escape. Now that's the two-dimensional picture, and it's pretty convincing. But again, do we know that this is valid in d dimensions? Well, yes, we'll do a proper proof now based on that picture using the triangle law. So I want to prove So now here comes the formal proof. I want to prove that every open ball in R to the D is an open set. I want to get all of them, so I start with let. I let A be any point in R to the D, I don't care which, and let capital R be greater than naught. That's a positive real number, and we don't care which. And we show that the ball, radius capital R, centered on A, is open. We've made no assumptions other than the fact that A is a point of R to the D and that capital R is greater than naught. So if we can prove that this is open, we've actually proved that every such ball is open, and we've done it. This is why when you want to prove something's true for all things of a certain type, you just let something be of that type, and if from that information you can get your answer, then you've proved it's true for all things of that type, which is a key thing that I'll be bringing up again in the session on how do we do proofs. Now, to show it's open, we have to show that every point of this set is an interior point. We need to show that every x in the ball is in the interior of the ball. Well, this is the same again. You let x be in that set because if we can prove it under those circumstances, then we'll be done. All I have to do now is prove that this x is in the interior of the open ball. This is an optional comment, this one. And I've already given you the formula that's going to work, but if you wanted to, you could take something smaller, but little r equals big R minus normal of x minus A will do. But let me note that first, I want to make sure it's a positive number, so since x is in BR of A, we have normal of x minus A is less than capital R by definition. So that means that that formula I gave you before does give you a positive number. So set little r equal r minus the norm of x minus a, which is what we expect is going to give you the distance. And at a good start, that is a positive real number, which is necessary. You're not allowed to take naught. That would be silly. And now, we now show that b little r of x really is a subset of the big open ball. And again, I put it in brackets because I think you can get away without writing that. How do you show that something is a subset of something else? You let something be in the first set. So it's another let. This proof is full of lets, and as they always are. Let y be in the small open ball. we've got to show that it's in the other ball. So this is, let y be the left-hand side, we'll prove y is in the right-hand side. To prove y is in the right-hand side, you've got to estimate the distance from y to a. Well, that's equal to the norm of y minus x plus x minus a. I've just rewritten the inside, I haven't changed anything yet. This is our standard trick. If you're going to, whenever we do one of these estimates for distances, we almost always end up using the triangle law, and you're going to estimate something in terms of things you already know. We know something about the distance from y to x, and we know something about the distance from x to a, and that's why we rewrite it this way. So that's smaller or equal to the norm of y minus x plus the norm of x minus a. That's by the triangle inequality. And well, the norm of y minus x is less than r. So that's smaller than r plus the norm of x minus a. But look at that formula up there for what r was. R was capital R minus norm of x minus a. So if you add norm of x minus a to it, you get exactly r. Now, if I'd done this without the diagram, you'd wonder how I chose which formula and so on. But with the diagram, it's obvious which formula will do. But notice we could have taken little r to be a half of that, and it would still have worked. If we'd taken r to be a half of the formula we used, it would still have been a positive real number. And making little r smaller only makes things better. So we'd still have been OK. We'd have been even a little bit safer at this point. But because we've got that less than there, we're still OK. And we do know that y is therefore within, strictly within distance capital R of A, so y is in the big ball. Right, so since that's true for all y in the little ball, that shows the little ball is contained in the big ball. So BR of x is contained in the big ball. And thus x is an interior point. As claimed. And again, you can unpick that a bit more. X was an arbitrary point of the big ball, so that shows the big ball is open and so on. But I think at this point we can say the result follows. So that's as claimed. You proved that every point in that ball is an interior point. So it's open. Okay, well, I've said more than you really need to say just to make sure that you can see the structure of the proof. But that's the proof in full gory detail with something like 3 let statements in. And that's how you prove that a Loban ball is open. A closed ball is not open. I'm not going to prove this. I'll just draw you the picture. So it'll be an exercise to check the details, but this will be a standard fact that you can quote. Let's draw you a picture of a closed disk. But think of this as the closed ball in R to the D instead. Centered on the point A, radius R. Then the interior of that, of the closed ball, is the open ball. And the interior well, what are the non-interior points, at least in this diagram, going to be? Anyone want to tell me what the non-interior points, at least in that diagram, would be, before we say the general? Any suggestions? If it really was a closed disk, what would the non-interior points be? That's right, it would be the boundary circle of the disk. That's right. And in the general setting, it won't be a circle anymore. If it was a ball, it would be if it was a ball in 3 dimensions, it would be the boundary sphere. And if it's in higher dimensions, then it's actually a quite complicated topological object. The boundary of the higher dimensional ball is quite an interesting sphere, sort of more generalization. You have to think of, in 4 dimensions, the boundary of the 4-dimensional ball is a 3-dimensional object, which is a little bit tricky to think about, though topologists do work with that sort of thing quite a lot. But fortunately, we can write down an exact formula for it. It's those x in R to the D such that norm of x minus a is exactly equal to capital R. And you can think of this diagram as a 2-dimensional cross-section of it. Obviously, the interior points are going to be the points at the edge of the set. So if norm of x minus a is equal to R, then x is going to be in the interior of the ball. If it's a closed ball, that is. Remember, the interior of the open ball is empty. So the interior of the closed ball will be all the points at the edge. There's quite a lot of sets in between the open ball and the closed ball, where you throw in some but not all of the points on the boundary. That's a bit like the half-open intervals in the real line, which are between the open interval and the closed interval. Well, of course, if it's a ball, then there's infinitely many sets in between, where you could just choose to throw in some of the points at distance r and keep some of the other ones out. And there's an unlimited number of variations you can throw on that. If it was a circle, you could throw in sort of various bits of arcs in various places on the boundary and keep other arcs out. And there's infinitely many choices. So there's lots of sets in between. If you do that, then the bits of arcs you throw in on the boundary are going to be the non-interior points of the set you get. The empty set and the whole of R to the D are both open in R to the D. Well, the easiest way to think about the empty set is probably to say it's got no non-interior points. And that's one of our definitions of open. So remember, U is open if and only if the interior of U is empty. So think about whether the empty set's got any interior points. Well, of course, it doesn't have any interior points. But nevertheless, every point of the empty set is an interior point of the empty set, because there aren't any. That's vacuously true. But because that's hard to think about, I think it's better to think about the interior. We know that id to the empty set is empty, so the empty set is open. And it's rather obvious that every point of R to the D is an interior point of R to the, is an interior point of R to the D. And so it's pretty clear that the interior of R to the D is equal to R to the D. If you did want to write a proof of it, you could take any radius ball you like and it'll work. Let me give you the one-line proof if you wanted a proof of that. Let x be an R to the D. Then the ball radius 1 centers on x is essentially by definition a set of points in R to the D. So x is in the interior of R to the D. That's how you prove it if you had to. Doesn't have to be 1. You could use any positive real number you like, and it would still work. That's a union of two open intervals. I'm not going to prove this in detail. I'll ask, as an exercise, get you to do this for yourself and check the details, but check the details directly. It's an interesting little exercise. However, it'll follow from results coming up in a minute. We know that open intervals are open. So that's an open interval. And 2, 3 is open in R. But this union is not an interval anymore. So we haven't yet proved this, but we're going to see in a bit that whenever you take a union of some open sets, you get another open set. So this will be a special case. So their union is still open. Though it's not an interval. So it's not an interval anymore, but it is open. And that's a special case of the fact that you can take any number of open sets you like and take their union, and it's still open. In fact, not just 2, but you can take infinitely many open sets and take the union, and it will still be open. In fact, it's even more than that, though we won't do that in this module. You can even take uncountably many open sets and take the union of an uncountable collection of open sets. It doesn't have to be even a sequence. It can be just as many open sets as you like. You can't stop being open by taking unions of open sets. Very different when we come to closed sets, coming up later. Unions of closed sets, only finite unions are safe. Infinite unions of closed sets can stop being closed, as we're going to see in a bit. A non-empty finite subset of R to the D is not open. Again, I'm not going to do a full proof of this fact. But let me just indicate for you what such a set looks like. It's got finitely many points in it. They could be anywhere. So here's just a few points. Let's call them x1, x2. Up to, say, xn. So note the word non-empty here. The empty set is a finite set, but the empty set is open. So amongst the finite sets, it's only if you've actually got some points there that you get trouble. And that's because those are the non-interior points. Every point of this finite set is a non-interior point. So say n is a natural number, and S is equal to, has got just n points in, then every point of S is a non-interior point. And S is not empty, remember, so S is not open. Again, it's an exercise to check the details, but you should be able to convince yourself that this really does work for any non-empty finite set in R to the D. Any questions on the example so far? So far we've talked about open sets and sets which are not open. We've got interior points, we've got non-interior points. Are there any questions about any examples we've looked at? Anything that I can clear up? Well, remember, you could always come and see me in office hours or after the lecture or send me an email. I'm always happy to answer questions on this stuff. You'll want to get on top of this stuff because it's relevant, of course. Really understanding all this stuff and being able to write proofs and being able to do examples is all relevant to the assessed coursework. So you will want to get right on top of all of this. Now, last time we already investigated what the interior points and the non-interior points were for the rational numbers and the irrational numbers, and we determined that the interior of each was the set again. So last time we saw the non-interior points in Q were the whole of Q, which is of course not empty, and the non-interior points in the irrational numbers, that gave you all the irrational numbers back again as well. So neither of these sets is open in R. And, well, so we've done open balls are open, which includes open intervals are open. Actually, you can check for yourself that the unbounded open intervals are open. But that's all a special case of this. The intervals are a special case of the D cells as well. So intervals have the intervals in R have the privilege of being both balls and D cells. When you go to higher dimensions, then the D cells have got sharp corners and the balls don't, so they're different. So the D cells we looked at before were open if we called them open. And if we didn't call them open, they weren't open. And you're allowed to quote that as a standard fact. But you might want to check the details for yourself again. And there's some information on this that would help you with that on a question sheet. But let me just, again, draw you a two-dimensional picture. E.g., if U equals 0, 2 cross 0, 1, the closed rectangle, Then you get this picture here, including the boundary. Then U is not open, and the interior of U is the boundary of the rectangle, whatever that means. We'll do boundary properly later. But once we've done boundary properly, you'll find that it does agree with what you expect. It's just the problem is, what is the boundary of Q and what is the boundary of Q complement? They are tricky. Whereas if you do the open interval, the open rectangle, sorry, so if U is equal to the open interval 0, 2 cross the open interval 0, 1, then you get a different picture. So this time you get dotted boundary or dashed boundary. This time the interior of U is empty. The interior of U is U, and U is open.